Now we'll take a look at what happens to cell EMF in non-standard state conditions. So we'll kind of go back through and remind ourselves of what standard state is. Standard state conditions are 25 degrees Celsius, 1 atmosphere of pressure for working with gases, solution molarity of 1.0 molar. So these are all of our conditions for standard state. So we're going to take a look at what happens with our equations for Gibbs free energy and the potential for the cell if we're not at standard state. Basically, what we're going to be doing is deriving what's called the Nernst equation. So we're going to start with our formula for Gibbs free energy. So we have delta G equals delta G at standard state, so Gibbs free energy at standard state, plus RT ln of Q. All right, if we plug in our values for our potentials, so we have at our non-standard state negative N Fe, our standard state negative N Fe0, plus our RT ln of Q. We do a little bit of algebra with that equation. We end up with the non-standard state potential for the cell. Right? So this is going to be the potential for the cell that that would be measured if you were going to use a meter to measure it. Would be the standard potential for the cell, the E0, minus RT over NF times ln of Q. So the ln of Q is going to factor in the concentration of the ions that are in solution. You remember those ions are also involved in that oxidation reduction reaction that's going to happen. And finally, a little bit more math with this. Trying to kind of boil this down a little bit to a more manageable formula. If we work in terms of log base 10 instead of natural log, we get this formula. If we're working at room temperature, 298 Kelvin, then that whole thing is going to boil down for us. So if we take that 2.303 RT over F, so that whole big thing boils down to this. We plug that into our equation, and we have the non-standard potential is our standard state potential that we can get from looking at our reduction potential tables, minus 0.0592 over the number of moles of electrons times the log of Q. And again, so Q would be the concentration of the ions that are participating in the redox reaction. So we'll take a quick look at one of the applications of this equation for figuring out the potential for a non-standard state cell. One of the things that we can do with this is create what are called concentration cells. So if I look at this, my nickel anode, so the anode is the loss of electrons. So at this electrode, we're going to have nickel going to nickel 2 plus 2 electrons. And our cathode is the gain of electrons, so it's going to be the nickel 2 plus 2 electrons going to nickel solid. Now, if we remember our reaction, our formula from the last slide, we have the potential for the cell is equal to the standard potential minus 0.059, sorry, 592 divided by N times log of the reaction quotient, Q. All right, so let's see what these numbers look like. Okay. Well, we know that the E0 for the cell, since we have the same reaction in both places, the reaction potential is going to be 0. The standard potential will be 0. Minus 0.0592 divided by the number of moles of electrons, in this case are 2 moles. So 2 down there. And then log. Now what is Q? Well, Q here is going to be equal to the concentration of the nickel ion on the product side, which would be this nickel here, or that one, divided by the concentration of nickel on the reactant side, which would be this nickel here, which has that value there. So if we plug those into the formula here, we have the 1 times 10 to the minus third molar solution on the top, and 1.0 molar concentration on the bottom. When you do the math here, you end up with positive 0.0888 volts. So simply by changing the concentration of the nickel ions on each side of the cell, we're able to create a potential difference here. Now, the cell wouldn't stay operable. It wouldn't operate for very long, because as soon as the process starts, you're going to increase the nickel concentration on in the beaker on the left, and the concentration of nickel on the right will go down until they finally reach the same concentration, at which point the cell would have a 0 potential. But up until that point, you would have a varying amount of potential, starting at 0.0888 volts and working down to 0. So this is a nice example of a concentration cell where you create potential simply because you change the concentration of the ions. Again, it's similar to what you look at in for an equilibrium. If you have a higher concentration of one side, it's going to shift and it's going to spontaneously move until you get to equilibrium. Well, that's basically what's happening here. So next up, we'll take a look at some of the other applications of oxidation reduction reactions, some of the more common things that we see in everyday life, and that should finish things up for us.